continuous probability distributions, and the normal distribution. In Chapter 6, we learned that a discrete random variable can only assume a finite or countable number of values with a break between successive values of the variable. So continuous random variables were symbolized by a capital letter X, and values that it could assume for example, would be x equals 0, x equal 1, x equal 2. And for that reason, they're discrete because there's no 0.5 or 0.75 or 1.2. Okay, we have discrete values, 0, 1, and 2. So for example, the number of correct answers on a multiple choice test, it could be 0, 1, 2, etc. These are all discrete values. The number of even numbers that come out on a dice roll, or on say several dice rolls, the number of even numbers that come out, we could have 0, 1, 2, 3, etc. So they are discrete in nature. So if we consider televisions in a household, again, also discrete in nature, x equals 0, 1, 2, 3, 4, etc. So it's impossible for a discrete random variable to have a value like 2.45. Okay, discrete variables are always going to have values that are whole numbers, such as these. Discrete random variable is a variable that comes from a random probability experiment. So it's impossible for a household to have 2.45 television sets. That's why they are discrete random variables versus continuous random variables, which we are going to study in Chapter 7. Okay, we had done a probability histogram in Chapter 6 for the number of correct answers on a 5-question multiple choice test. So if the experiment involved guessing all 5 questions on a multiple choice test, the number of correct answers for x, the discrete random variable x, can assume values of 0, 1, 2, 3, 4, or 5. So you could get none correct, or you could get all 5 correct, or any number in between. The height of each rectangle represented the probability of that event happening. So the probability that you guess on all 5 answers and you get none correct has a probability whose height is the height of this rectangle, which is 0.2373. The probability that you guess all 5 answers and you get 1 correct, 0.3955. We could also answer the question, what's the probability that you guess all 5 answers and you get at most 1 correct? That would be the sum of 0.2373, which is this rectangle, plus the value 0.3955, this rectangle. Okay, so this was a probability histogram for the probability distribution of number of correct answers while guessing on a 5-question multiple choice test. Okay, the random variable was number of correct answers on a 5-question multiple choice test. Each question had 4 choices. So do you remember how we arrived at these probabilities? We used the binomial probability formula. Number of trials was 5. The probability of getting a question correct was 1/4 because each question had 4 choices. And the number of successes is basically all the values of x. We did this 6 times, so we changed the number of successes to 0, and we got this binomial probability. We changed the number of successes to 1, and we got this binomial probability. So reading the chart, or reading the histogram, what's the probability of getting 1 correct answer? So you should look at x equal 1, look at the height of the rectangle, 1 correct answer is 0.3955, which is the probability. Okay, 0.3955 or 39.55%. What's the area of this rectangle? Well, the area of a rectangle, the formula for area of a rectangle is length times width. So let's think of the width of this rectangle. If this is 0 and this is 1 and this is 2 and each rectangle has the same exact width, then the width of the rectangle is exactly 1. Okay, the width of each of these rectangles is exactly 1. The height is 0.3955. So if we multiply width times length, or width times height, however you want to think of it, it's going to be 1 times 0.3955, which is 0.3955. The area of the rectangle is the same as the probability. What's the probability of getting 1 or 2 correct answers? Well, to answer that question, we take the probability of getting one answer correct, which is 0.3955, plus the probability of getting 2 answers correct, which is 0.2637, and we add them up. What are the areas of these 2 rectangles? Well, the area of the first rectangle we discovered was 0.3955 because we take the width times the height, 0.3955. The area of the second rectangle is going to be 0.2637 because we take the width, 1, times the height, 0.2637. So if we add up the 2 probabilities and we get 0.6592, then if we were to add up the 2 areas, we'd also get 0.6592. So the sum of the 2 areas is the same as the sum of the probabilities. Okay, the sum of the areas is the same as the sum of the probabilities. Look what happens when we add up the areas of all the rectangles. So basically what we're doing is adding up the probability of getting 0 correct, plus the probability of getting 1 correct, 2 correct, 3 correct, 4 correct, and 5 correct is kind of hard to see because it's only 0.0010. If we were to add up the sum of all these rectangles, you should recognize from a probability distribution that the sum of all the probabilities is always 100%. So if we add all these up, we'd get 1 or 100%. Now we're going to discover an important relationship that exists between area and probability. The probability of an event occurring is equal to the area of the rectangles that cover that event. So the probability of getting 0 correct is the same as the area of the rectangle for x equals 0. The probability of getting 3 correct is the same as the area of the rectangle for x equals 3. The probability of getting at least 2 correct is the sum of the areas of the rectangles for 2, 3, 4, and 5. At least 2 means 2, 3, 4, and 5. Okay, so the sum of the probabilities of the rectangles is the same as the sum of the area of the rectangles.